Welcome everyone to the lecture 16 of week 6 of climate change extreme events course. In the previous lecture we have talked about different types of risk assessment or different types of, let us say, what are the differences between hazard, risk and vulnerabilities, like that. We have also talked about how do we implement this framework in order to quantify the risk of different places in terms of growing concerns related to climatic extremes or hydrological extremes, like that. Then we have also talked about different types of data set which we can use it for quantification of these different types of risk in different parts of the country, like that. In this lecture we will primarily focusing on the written period quantification. Why it is important? Because whenever we are talking about climate extreme risk or hydrological risk, it is somehow related to some sort of high magnitude or very low magnitude events. When these events are related to very high magnitude or very low magnitude events, we have to know about what is their frequencies, what is their pattern, what is their occurrences, what is the likelihood condition that a particular event can occur in a particular location. So, therefore, a written period estimation is one of the key important parameter when we are dealing with some sort of extreme analysis or risk assessment of climate extremes, like that. So, when we are talking about the written period, it is nothing like the magnitude. It is a kind of a magnitude, but we are also referring to a specific type of magnitudes based on their written periods. For example, there are several written period magnitudes of climate extremes which can occur in within 100 years, or let us say 500 years, or let us say 1000 years, or let us say very short span like 20 years, 15, 10 years, 5 years, like that. For different written periods we have different magnitudes, and based on different written periods years, we quantify their magnitudes, and based on that we basically propose the risk assessment or solution for one particular locations. So, suppose when we are interested in providing some sort of short term events in a certain location, we are primarily looking at those events which has a higher frequencies, or which is the written period years are lower in nature, or if you are talking about a long term solution or long term planning of a certain structure or certain measures, we are essentially looking at those extreme events which occurs relatively larger time scale, 100 years, 200 years, like that. So, therefore, it is very important to have understanding about written periods and their magnitudes and their relationship, so that we can have a better management or risk assessment of a different region. So, in this lecture we will primarily focus on defining the written periods and their significance in the risk assessment. We will understand the statistical methods which are there for estimating the written periods. We will also explore role of extreme value theory, which we have already covered in the previous classes. How do we use that extreme value theory in order to let us say quantify the rare events or their magnitudes or their probabilities, like that. And then based on their relationship, when we establish it, how do we calculate or written periods of whatever we are desiring. For example, lower frequency event or higher frequency events, like that we can calculate based on those relationship. So, before moving into that complex relationship, it is very important to understand about what is exactly written period. What is written? We have talked about multiple times that 100-year written period flood, or 50-year written period flood, or 200-year written period flood. What is exactly written period? Written period basically refers to the average time interval between occurrences of an event of a given magnitude or intensity, such as floods, storms or earthquakes. So, written period generally we can, so let us say we have identified the maximum magnitude of different flood events or extreme rainfall events or temperature events. which is exceeding certain thresholds or based on our criteria, what we are doing basically we are calculating what is their inter-arrival period, and then based on that return period or inter-arrival period we calculate what is the average value of rainfall amount. Let us say it is exceeding above 100 mm rainfall or 200 mm rainfall daily basis, like that. So, this is how basically we calculate the return period. This is the definition of the return period. It is used in the risk management because when we know about let us say what is the magnitude of extreme events and what is their probability, then we can ensure or estimate how often an event can occur, and then therefore we can plan certain different risk mitigation structures or non-structural solutions. For example, if you are talking about let us say there is a 100-year flood event, which means that the flood has a 1% chance of occurrence in any given year. So, for example, if you are talking about 100-year flood event where we know that magnitude, certain magnitudes, then for that certain magnitudes this particular year the flood will occur every year, the chances of that particular flood event is 1%. That is what exactly in a very simpler form we can understand about 100 years flood meaning of that. Similarly, you can talk about 50 years, you can talk about 10 year, you can talk about. So, if you are talking about 10 year, it will be like 1 by 10, it is basically close to 10%. So, 10% chances a rainfall or a flood event can exceed or can be in that magnitude based on that our calculations like that. So, here it is the calculation is written here. So, you can see 100 year means 1%, 50 year means 2%, 25 is 4% chanced in a given year every year, 10 is 10%, 5 is 20 and 2 is 50%. 2-year return period generally also called as a median, median floods or extreme events like that. There are certain misconceptions about return periods. For example, if I am saying a 100-year flood only happens once every 100 years, this is not correct, because when I am saying 100-year is about probability not frequency, which means on an average such event has a 1% chance of occurrence in any given year, or not that it will not only happen once in a century. It means we have 1% chance of a particular event will occur every year, not exactly that ki if a 100-year event occurred, the same 100-year event occur after 100 years after that. No, this is not correct. 100-year, the second misconception is a 100-year flood cannot happen in the same place more than once in a 100 years. So, again if you go back to this definition, 1% chance, it is possible that 100-year flood can occur more than twice or more than once in a 1 year particular year, and it is also possible that this can happen consecutive years also. So, therefore, it is basically these are the two misconceptions which is related to the return period estimate. How do we calculate return period? So, let us say you have know the probability of occurrence of any particular extreme events in a given condition. Higher the probability, higher the return period, the lower the probability, which means the probability and the return period has inversely relationship. If P is higher, T will be lower, and T is higher, P will be lower, something like that. So, for example, if you are talking about average interval between occurrence of the event, for instance 50-year flood means that on an average a flood that magnitude is expected to occur once every 50 years like that. So, here it is a very simple calculation which I have provided here. For example, probability is often expressed as a percentage, 2%, 50 year. Before moving into this particular example, I would also like to add here, when you are talking about probabilities, probabilities are values which are in between 0 and 1. It cannot be greater than 1 or it cannot be negative numbers less than 0. If it is 0, which means the occurrence is almost nil, those event has not been occurred in the data set whatever we have. If it is 1, means 100% probability of occurrences. Suppose a event has a probability is equal to 0.5, which means every year or within the data set the 50% chance is that event will occur. If it is, let us say 0.01, which means it is around 1%, every data point might have a probability equal to 1% if to that particular event like that. So, this is how basically you can understand about probabilities and return period relationship. If a return period, let us say 50 years, the chance of the event occurring in a specific year is 1 by 50, which is equal to 0.02 or 2%. This means that on any given year the event has 2% chance of occurrence, that is we can basically calculate it from this formula. So, what is the message here? Basically, if you know the probability of each event, you can simply calculate the return period. If you know the probability of different magnitudes of flood or different magnitudes of extreme rainfall events or cyclone events, magnitude of cyclone events, or let us say any other different climate extremes, you can convert you into the return period. It is a simple graph which shows that probability densities. When we are talking about probability density functions, it generally calculates the probability density, not probability values directly, and therefore, we have to calculate the probability density into the probability value, or simply you can use the cumulative distribution function CDF functions, and that can give you directly the probability values and can be used for probability estimation for different magnitude of events, and then you can convert into your return periods. Now, the question is, how do we calculate return periods? What are their approaches? There are two major approaches. One is empirical approach, second is statistical approach. Empirical approach is very simple. Let us say you have a historical records of some events, floods, hurricane, etc., and you wanted to estimate the return period. The method is works best when sufficient amount of historical data is available. What are the steps in empirical approach is, we have to rank the historical event by magnitude. Suppose you have gathered the data of magnitude of events, any events, climate extreme events, peak discharge for floods or maximum wind speeds or hurricanes like that. Sort these data events from the largest to the smallest. So, we have to you have collected the data, it is possible that data might have a mix of values, some is lower, then higher, then moderate, lower, higher, something like that. So, you have to sort this data set from the highest to the lowest, largest to the smallest, like that. So, at the first column you have the highest value, maximum value, at the last column you have the last row you have the lowest or minimum value for that. Once you arrange the data like that, you can assign the rank. So, even so for the largest event you will give 1 rank, and the smallest event you will give the total number of data points. Let us say you have 100 data points, the smallest magnitude of events will have 100 rank value. Once you have arranged this data in this way, you can calculate the probability or return period based on this particular formula. T is equal to n plus 1 divided by m, where n is your number of records. Let us say if you are talking about 100 years, so n is equal to 100 and m, small m is equal to rank. So, for example, if you are dealing with the largest flood, m will be 1, and if you are talking about, let us say, smallest flood, given the condition that you have the data set is 100, the m will be equal to 100, like that. So, this way if you fit the data in this particular formula, you can basically calculate the return period of your magnitude of different events, and then you can calculate or relate with. You can make a regression analysis between return period plus your magnitude, and you can plot the figure like that. We will see that analysis in our assignment part probably. The second approach is called statistical approach. Statistical approach, in the previous lectures we have talked about several different distribution functions, in which distributions we have also talked about some sort of extreme value theory or extreme value distribution functions. These extreme value functions or distribution functions are very important in order to assess the nature of the distribution of your extreme events. So, what we have to do in the statistical approach, we have to fit the extreme value distribution to the data. For example, we can use the generalized extreme value or the log Pearson type 3 distributions or any Gumbel, Fritchett, or let us say Weibull, these kind of distribution you can fit and you can model the extremes. What do we mean by model the extremes? You can identify or you can find out what is the probability of occurrences with their magnitudes, their relationship. Once you calculated the estimate the exceedance probability, probably using the cumulative distribution function, you can basically assess what is the probability of exceeding the flood magnitudes or the rainfall extremes above certain thresholds, and using that particular probability value using the CDF function, you can calculate the return period. You can just divide the 1 by p and you will get that the return period magnitude. This is how basically one can use the statistical approach to also quantify the return period and their magnitudes based on the data set. So, this is some of the example where we have collected multiple year maximum magnitude, and we have already ranked them. All these extreme rainfall, extreme climatic events. So, for example, the top one has the maximum magnitude and the bottom one has the minimum magnitude. We have arranged like this, we have given the rank, and then based on the previous empirical formula, we have calculated the probability, and reverse of the probability we have calculated the return period. For example, here if the event is equal to 5.08 something like that, the return period is 19 years. So, 19 years is your return period. You can also convert this 19 years value into every year percentage, and that will give you what is the likelihood scenario for an event to occur every year like this scenarios like that. These are the some of the distributions which we basically generally used for modeling the extreme value analysis, which we have already covered. This is just a revision. Basically, we have let us say extreme values. We can use the Gumbel distribution or extreme value type 1 distribution, where we are talking about mostly the maximum or minimum sample of values, especially for modeling extremes like maximum daily rainfall or highest temperature recorded in a year. We have to fit the data in this particular distribution function, or maybe we can use the generalized form of this extreme value distribution, which is called generalized EV, where we basically used all these different types of type 1, type 2 and type 3 all together, and to model the extreme events and their quantify their probability of occurrence. Or maybe we can use a log Pearson type 3 type distribution, which is also often used for modeling the hydrological extremes such as flood events or different types of climatic extremes also. That can be basically log transform data set and model your Pearson type 3 distributions. That is what their back end mechanism is. So, once you identify the suitable type of distribution for your extreme time series data set, what is the next step? The next step is we have to find out the goodness of fit test. We have to find out whether whatever the distribution you have selected for the data set, is it fitting with your data set correctly or not. So, you can use KS test, Anderson and Darling test, chi-square test or likelihood ratio test, LR test we also say. Based on these tests, we can find out the goodness of fit of your distributions. So, this will give you some value. With you compare the reference value, you can see whether your fit is appropriate or you have to change the distributions or not. Then there is another method which is used in while you fitting the data set in these distributions. that is called maximum likelihood estimations. So, maximum likelihood estimations is basically estimation of the parameters of these distributions by maximizing the likelihood of different events or distributions like that. And there is some sort of graphical approaches which is also used to graphically assess whether when you are fitting a distribution to your data set, whether it is correctly modeling your extremes or is it away from your extreme data set like that. You can use the quantile plot, that is called QQ plot, which is basically comparison of the quantile between all these theoretical and these types of data set, or maybe we can use the probability plot, where we basically calculate the probability of the data set and the probability of your theoretical model, and then you calculate for different events, and then you make a probability plot, and then you can make it one by one line, and you can compare whether your fit is up to date or appropriate, or you have to change your distributions like that. Then so this is one example of the Gumbel distribution which is widely used for modeling extreme events. This is also we call extreme value method. Is especially designed for different types of events like floods, droughts and temperature extremes. So, what is the overall procedure in Gumbel distribution applications? We have to understanding of the return periods, we have to use these types of distribution for return period calculation. We can also use these distribution for modeling purposes. Let us say you have limited amount of data set, and now we do not know exactly about what is the value of 100-year return period flood. You can simply use this Gumbel distribution function, and then you can calculate what is the magnitude when the probability is equal to 0.01 for 100 years, or even we can go further beyond 100 years, irrespective of that whether you have the data set for 100 years or not. But we have to use this analysis with caution, because if you are extrapolating that analysis, that might give you some underestimation or overestimation as well. Predicting the magnitude of future extreme events, you can also use upcoming extreme events for Gumbel distribution and can predict what is likely to be happen in future conditions. So, return period estimations are very important aspect when we are dealing with the risk assessment, but when we are dealing calculating the return periods, it is also essential to know that we should have a proper understanding about what is the uncertainty or confidence whatever the return period we are calculating from our data set. So, where this uncertainty can be originated in the data or your return period estimate. For example, limited historical data. We have 25 years data and you are trying to calculate the 100 years return period flood. That might create some sort of problem or higher uncertainty. Therefore, you have to have a appropriate historical data set. Largely we consider, if we are let us say calculating the 100-year flood, we have to have the data at least for 50 years or more than 50 years like that. Then you can appropriately calculate the 100 years flood. If you have 25 years, 20 years, 30 years like that, it might give you more uncertainty compared to your 50 years records like that. Short data records is one of the problem. Sometimes you have sparse data or missing data or very rare events, which might also create some sort of problems in your fitting of your distributions. Climate variability and non-stationarity, which we have already discussed, that non-stationarity if is there, that might hamper your probability distribution fittings, because your extremes behavior, statistical properties of your data set where you have extracted these extremes have been already modified, and therefore, if you are considering all these extreme values in a single distribution, that might give you not a correct result, and therefore, non-stationarity is a problem when we are dealing with the calculating the return period. So, we have to make sure that your distributions or data sets should be free from non-stationary conditions before fitting of these data set. Climate variability, which is basically the major cause of these non-stationarity. So, therefore, you have multiple these regions where you can have uncertainty in your predictions when you are applying some sort of distribution functions. How do we quantify these uncertainty? you have to apply the confidence bound. So, when you are calculating, let us say, maximum likelihood estimation, maximum likelihood estimation always gives you the parameter value in a range, and you use generally middle value or mean value or median value, like that. So, if you use multiple values of your maximum likelihood parameters, let us say mu, sigma and eta, then you can get an idea about what could be the confidence interval of your return period, how much the values can vary from, within your confidence bounds, like that. Similarly, you can calculate the error, and then you can calculate the variation in the data set. Or the another approach, let us say if you have short term records, how do you increase the records? You can use the bootstrapping techniques, resampling of the data set, and then you can estimate the periods, because this way you have already created more number of records, and therefore it might be possible that you have lesser uncertainty when you are calculating the return periods using these types of records, like that. Okay, so this is all about return period estimations, their confidence interval, their uncertainty estimation, and their error bar or error estimations, like that. Why do this matter? Why it is important to have a proper understanding of return periods? Let's suppose you are planning, so you are planning for a bridge or planning for, let's say, a reservoir or dam in a certain location. Why it is necessary to build a dam in certain locations? You are planning to protect the downstream part of the region from the flooding events. So, these dams can store excess water which is coming from the flood event and can store in the reservoir capacity and can release these water gradually, not during that flood higher intensities, like that. So, in a way, these dams and reservoirs are modulating the peaks of your discharge events and lowering down the peak. Therefore, the floods impact should be a little bit mitigated or should have a little less effect compared to the higher upstream regions, like that. So, that is why these dams infrastructures are very important in order to protect the population from growing risk of the floods in the downstream part of the region. Let us suppose you are planning to build a dam on a particular river. You need to have a proper understanding about what is the magnitude of 100-year flood event in that region. Why it is important? Suppose you have flood event occurrence in a different years, the probability is 1% chance, and if you have miscalculated the 100-year flood magnitude, and the design you have made the design based on your calculations, and it might possible that the 100-year record flood is little bit higher in the magnitude, you cannot accommodate that excess water in the reservoir, and that can create upstream flooding and downstream flooding or complete failure of the reservoir operations there. Or sometimes it is also observed because of the higher catastrophic event that can also impact the reservoir construction material and can also break down or significantly affected the infrastructures also. So, therefore, it is very important to have understanding about this return period. Or let us say if you are talking about urban flood is largely the process of your extreme rainfall. So, then you have to have a sewer system or storm drainage network based on different return period rainfall events. Suppose you are talking about 100-year return period, 50-year return period, so that you can prepare for a storm drainage system, so that if excess amount of water will come, it will smoothly can evacuate from a particular city, so that it will not create some sort of urban flooding problem in a certain. So, therefore, these extreme the return period calculation with their probabilities are very, very important. So, infrastructure design, for example, dams, bridges, drainage system, we have to take care of these things, and therefore, we need to know about exactly what is the return period. For example, we are talking about zoning laws, or which area has a higher risk of flooding, higher risk of urban floods, or higher risk of, let us say, drought events, or multiple high risk of cyclone events, zoning. So, that way if you know about the magnitude and probabilities, you can basically provide the zones, and based on that you can make some sort of laws or policies, so that you can restrict some sort of activities within that zones which are higher severity levels, like that. Floodplain management, it is a very important issue, because floodplains are the region which are highly encroached by human activities, and when we know about different types of flooding events or the return periods or probabilities, we will be also restrict those activities which is happening close to the river. I will give you one example. If you if you read about, let us say, Uttarakhand flood, what happened there. So, lots of activities, human constructions was made within the channel floodplain areas very close to the river channel, and therefore, in 2013 when this flood occurred, it completely vanished all these infrastructures there, and therefore, severe loss of human life and infrastructure was reported there. Insurance assessment is also very important, because we have to provide the insurance schemes or remunerations, or let us say sort of the payment of what the people have lost, or crop insurance, for example, infrastructure insurance, like that. So, this is what we have also calculated based on their vulnerabilities, severities, and based on the return period exposure to different types of extreme events. So, in a nutshell, basically risk assessment, design standards, construction regulations are the ways we are talking about basically calculating the these return periods and all. What is the challenges in return periods? As we have already discussed, short historical records that might create some sort of major issues when we are dealing only the short historical records and calculating the return periods. Stationarity is another problem when we are not dealing with the stationary time series data set, and it might have some non-stationary behavior that can create some sort of uncertainty in your return periods. For example, we are saying that rainfall extremes are continuously rising. So, in that sense, if you are using the trend time series in your frequency analysis, that might produce not exactly the correct return periods. We have to take care of those stationarity assumptions. How do we improve this? Incorporating the climate projections, or assessing the more number of historical data set, or stationary or non-stationary GV models, or non-stationary approaches can be applied to model the extremes. So, in the summary, in this lecture we have talked about what is return period, how do we help use these values to assess the likelihood of rare extreme events. We have also talked about different types of empirical and statistical methods which basically can use to estimate the return periods from the historical data set, and we have also talked about different limitations and their uncertainties which we have to take care when we are applying the extreme value distributions, and how do we improve them. For example, we can climate change impacts, or some sort of projections, or some sort of non-stationary models, or increasing the historical data set, like that we can basically improve our understanding, and then we can have a better return period and magnitude estimates that will be helpful for our risk assessment. In the next lecture, we will talk about the uncertainty analysis in climate projections, and we will also talk about how do we use those projections for risk assessment. Thank you so much for your attention.